Yeah, next we have Kristinn Thórisson from the great nation of Iceland, who will tell us about AI evaluation and his thoughts about a task-oriented framework for this with the AI and AGI and lots of other good stuff. So.
Yeah, thanks, Ben. Good to see you all, and thanks for coming to this session. I'm going to be talking about two things that are kind of burning in my mind that I really wanted to tell you about. And if you guys, I'm going to keep this pretty short, so if you guys find any of this interesting, please tap me on the shoulder afterwards. We might have some time for questions as well. But how long do you have, Ben? Is it like 20 minutes that you're?
15 or 20
15,
minutes.
20, yeah.
Yeah.
Okay, good. So we should have some time. So I'm going to start with a couple of unaddressed needs for AGI. Most evaluations that we've been talking about using for AI systems involves measuring the performance of the system at a single point in time on a well-defined task. There's nothing wrong with that, really, but it means that if you want to compare, say, two systems that were developed, say, years apart, or two versions of the same system, you have to be sure that you have the same task, and you have to do it exactly the same way, otherwise you can't really compare the performance. And so that's a problem, but a even deeper problem, and Julian actually addressed some of these, and I was very happy to hear that. We don't really have, we haven't been talking a lot about, in the community, about how to measure, for instance, learning capacity. I mean, like speed of learning, the size of memory, and so on. We talk a lot about reaction time, but it's really, we don't have a really good idea for reaction times to what. Most of the times it's like blinking lights. But reaction time, for instance, as to you walk into a crowd and suddenly you realize you're in the wrong meeting room and you look like an idiot. And what's your reaction time for figuring out what to do at that moment? So we don't really, we haven't really gone very deep, and you can't really look at psychology for any answers because they don't really have the same interests and needs as we do in AI. Lifelong learning and forgetting, you're going to have this, all systems are going to have limited memories. Well, what do you do about that when you're bumping up against your capacity? Are you smart about your forgetting? We don't have any measures for that, as far as I know. Transfer learning, certainly this is a huge thing for AGI that is completely irrelevant to systems like intelligent temperature controls, which have a very well-defined task, and you're not going to ask them to do anything else. They're just stuck on the wall there. It doesn't matter how much smarts, suppose it's smarts are in them. And then cognitive development, humans and probably animals, some animal species as well, go from being able to do some very simple things very badly to reaching these various milestones that Piaget was very good at making people aware of, that you can see very clear developments in the capabilities, the types of things that the minds can do. So these are some things we have to think about in AGI. So one of the things that I think kind of follows on to what Julian is talking about, which is, okay, we're taking, first it was chess, and we worked, the field worked on that for a long time. And every year they predicted, it's going to be 10 years till champion is beat by a machine. And then it was AGI, and now it's video playing. And so we're slowly progressing towards proper ways of constructing and evaluating AI systems. But what would be really great is, I think, is if we had a construction kit, sort of like a Lego kit, where you could pick out things, put together various tests, and really understand what the tests mean, what their function is, how they compare to other tests, and so on. And we wrote a paper about this last year, actually, last year's AGI. So what we would want from such a framework is it should allow you to easily construct abstract task environments and variants thereof, where if you're not too interested in the lowest level, the actual pixels, let's say, or the actual design of the board, whatever it is, the type of task you have, that you could design equivalent tasks with variations where the hierarchy sort of allows you to do things at various levels of abstraction. So, for instance, you could say, okay, I'm going to do a bunch of tasks. I'm going to create a bunch of tasks here that are very similar to, say, maze following or solving. And you could rig these up in a way that you could press a button and you could automatically test systems and easily evaluate the outcomes. And this is sort of actually, it's very, very much along the lines of what Julian is talking about. In fact, I'm just taking it one step further. Let's not just talk about games. So let me just give you a couple of things about what the desired features of such a framework should be. You should be able, so it should have a bunch of knobs, this framework. And you can basically tune the amount of determinism, periodicity, and continuity. So, if you want to have a discrete system where you have a checkered board in 2 or 3 or n dimensions, you can do that at some granularity. But if you want it to be partially continuous, if there are some, for instance, you want to do a task that is akin to throwing a frisbee at a dog, well, the frisbee doesn't move between points in space, it moves continuously. And the dog's speed needs to be at a certain level, and it needs to jump at a certain point in time. And these are have some variations that you can, that the dog can work with. But if your AI is like that, it's working with continuous variables. You should also be able to do that. You shouldn't be stuck with these board games now, or discrete states. Asynchronicity, so things should be able to happen simultaneously. Dynamism, you should be able to control how much is moving in the world. Board games tend to be completely still while you're thinking. The real world doesn't work like that. Observability, you should be able to control how much of the environment is observable actually by the agent solving these tasks. So that to make it harder, you can hide some variables under the hood that are not observable, but are nonetheless causally connected to observable things. And the amount of control that the agent has that's supposed to be tested, multiple parallel causal chains, there's a bunch of waterfalls, someone throws something in one stream, it flows over down into the lake, etc. You might need to collect things from various parts. I'm just taking that as an example. And as well as the number of agents in that world. So that's a sort of that's a picture of a very flexible framework that allows you to construct things and then automate testing. And it shouldn't be just limited to video games or just to board games. It should be more general. But to be able to do that, and this is the second half of my burning issues, we have really no underlying theory here. of tasks. So that is strange because really we talk about tasks all the time in AI. In fact, 99.999% of all AIs built today are built due to a very, very specific idea of a task that we want them to solve. So evaluation is done a lot ad hoc, and people build the AI, then they say, oh, well, it's really good for this, and not so good for that. So let's build a task that allows us to make it do those tasks that it's good at, and we'll use those to evaluate it. And and that's a general pattern, and you end up with all sorts of results that you can't really compare. So you don't know if AlphaGo is any better than Deep Blue. Well, you do have some idea because it's not. These systems are not supposed to be general purpose systems, but in AGI that is not the case. So this is why we need an underlying theory of task. And a task is a central concept in AI that's loosely ill or really undefined, in fact. So here's the list of things that I think, a nice Lego kit of, and I consider it because I used to work at Lego, of like a task environment construction kit should have. And a good task theory would essentially give us the way for how to build these knobs, how you could flexibly tune and set these. So, and the problem is, I think, very much in AI that we've been thinking so hard about how to test if a system is intelligent, starting with the Turing test. I mean, a lot of these ideas were brilliant for their time. Some of them even currently very brilliant, but they only look at a very narrow slice of the pie. So I think now we need to turn to this concept, task, and hopefully create a theory of it. And the main purpose, I'm just going to focus on this. There are several reasons, I think, for why we should do this, but the main reason is for proper evaluation. And evaluation is not just for showing how AI can beat humans at some limited task. Evaluation is also used for the whole field to understand its progress. We want to compare one system to another, even several years apart, in the same team or between research teams. We want to compare versions and measure progress on various dimensions. And for all of this, we really, so we really need evaluation, but to do proper evaluation for AGI, we can't just take the standard way that simple AIs, classical AI, if you will, systems do it, because there the task is really clear. It's not so hard to get a grasp on what that task is. To test your AI for that task, you just have it do the task. But in AGI, what we want is general systems that can do unanticipated tasks, even tasks that the designers never foresaw. So how do we evaluate these systems? It is just an illustration to elucidate this. So if you have an agent, a task, and an environment, each with a number of dimensions that can be set to, or variables that can be set to some value, all right? If you want to evaluate just the agent's performance, you can't have a bunch of the variables on the task and the environment be changing all the time. You have to fix them. So for an agent, for agents A1 to AN, with running on various tests and evaluations, you must hold the task and the environment constant, or you must have a proper theory of how tasks and environments work so that you can basically, via the theory, annul their interaction with the agent, with the various settings. And this is not possible to do without some understanding of what tasks are and how they work. A way to compare one task to another. A way to say, okay, this task is different to that task in this and that way. That should have an effect on our agents in such and such a way. I guess this is the main slide here. A task theory should support comparison of similar and dissimilar tasks. So across a wide spectrum on various dimensions. Abstraction and concretization. So if you have an abstract description of a task, you should be able to, via the task theory, to come up with a set of tasks, concrete tasks, that you can say belong to that abstract class of tasks. It has, it's in that same space in the n-dimensional same position in the n-dimensional state space. It should allow you to estimate time, energy, cost of errors, and all sorts of other really important things. And really, it should give you some measure of complexity of tasks. If you want to compare tasks, well, you've got to also have a way to decompose tasks. In which case, and this is why I use the Lego box, in which case you also have a way to compose tasks. So this might be one of the major ways in which you would achieve a way to compare tasks. All right.